Welcome students to the sixth lecture on the chapter atoms. In lecture 5, we had discussed the introduction of atomic spectra, then the spectral series of hydrogen atom. We had also discussed the concept of excitation and ionization of atom. And finally, we dealt with the de Broglie's explanation for Bohr's second postulate. In this lecture, let's work on the numerical on the chapter atom. Let's go on with the first. The radius of innermost electron orbit of hydrogen atom is 5.3 into 10 to the power of minus 11 meter. What are the radii of the n is equal to 2 and n is equal to 3 orbits? In the question we have been given the radius of innermost electron orbit of hydrogen atom as R0 is equal to 5.3 into 10 to the power of minus 11 meter. And we know that the radius of nth orbit is given as n square into R0. The radius of n is equal to 2 orbit of the hydrogen atom is R2 is equal to 2 square into R0. If we substitute the value of R0 in this, we get the value of radius of n is equal to 2 orbit of hydrogen atom as 21.2 into 10 to the power of minus 11 meter. Similarly, the radius of n is equal to 3 orbit of hydrogen atom is R3 is equal to 3 square into R0, where R3 is equal to 47.7 into 10 to the power of minus 11 meter. So thus we have found the radii of n is equal to 2 and n is equal to 3 orbits. Let's go on to the next. Using Bohrs model, we have two sub-questions. A. Calculate the speed of the electron in a hydrogen atom in n is equal to 1, 2 and 3 levels. B. Calculate the orbital period in each of these levels. Let's work out on the first sub-question A. Now, speed of an electron in nth level or orbit of hydrogen atom is Vn is equal to E square divided by 2n epsilon naught h. Now, in this, we know E is the charge of the electron, epsilon naught is permittivity of free space, and h is Planck's constant. Now, the speed in first level of hydrogen atom is given by an equation V1 is equal to E square by 2 epsilon naught h. By substituting the values of E, epsilon naught and h, we get the value of V1 as 2.18 into 10 to the power of 6 meter per second. Then, speed in second level is given by an equation V2 is equal to E square divided by 2 into 2 epsilon naught h, which can be written in terms of V1 as V1 by 2. So therefore, V2 is equal to 1.09 into 10 to the power of 6 meter per second. And speed in third level is V3 is equal to E square divided by 2 times of 2 into 3 into epsilon naught h, which can be written as V1 by 3. So hence, V3 is equal to 0.73 into 10 to the power of 6 meter per second. We have found the values of speed of an electron in first level, second level and third level of hydrogen atom. Let's move on to the second solution for section B. Now, the orbital period of an electron in nth level is given as Tn is equal to 2 pi Rn by Vn. The radius of nth orbit is Rn is equal to n square into R0, where R0 is 0.53 angstrom naught, which is also called Bohr's radius. So therefore, orbital period in first level is given as T1 is equal to 2 pi R1 by V1. By substituting the respective values of 2 pi R1 and V1, where V1 is obtained from the section A as 2.18 into 10 raised to 6 meter per second, we get T1 as 1.157 into 10 to the power minus 16 seconds. So hence the orbital period of an electron in first level is 1.157 into 10 raised to minus 16 seconds. Similarly, orbital period in second level T2 is equal to 2 pi R2 by V2. So which can be written as 2 pi into 2 square into R1 by V2. So if we substitute the respective value of R1 and V2, we get the value of T2 as 1.22 into 10 to the power of minus 15 seconds. Thus, the orbital period of an electron in second level of hydrogen atom is 1.22 into 10 to the power of minus 15 seconds. Finally, orbital period in third level of an hydrogen atom is T3 is equal to 2 pi R3 by V3. On substitution of the respective values, 2 pi R1 and V3, we get T3 is equal to 41.03 into 10 raised to minus 15 seconds. So these are the three values of orbital period in the levels 1, 2 and 3 respectively. Let's move on to the next. The ground state energy of hydrogen atom is minus 13.6 electron volt. What are the kinetic and potential energies of the electron in this state? So we have been given the total energy of a hydrogen atom in ground state as E is equal to minus 13.6 electron volts. The relation between the total energy and the kinetic energy of our state is K is equal to minus of E. So since E is minus 13.6 electron volt, minus into minus becomes plus, hence kinetic energy of an electron or of the hydrogen atom in ground state is 13.6 electron volts. Now, the relation between the total energy and potential energy of a state is given as U is equal to 2 times of E. So hence U is equal to 2 into minus 13.6. Potential energy U is equal to minus 27.2 electron volts. So this is how we calculate the kinetic and potential energies using the given value of total energy. Let's move to the next question. A difference of 2.3 electron volts separates two energy levels in an atom. What is the frequency of radiation emitted when an atom makes a transition from upper level to lower level? Now here, the energy difference between the two levels is delta E, which can be taken as E1 minus E2, which is given as 2.3 electron volts. So if we try to convert electron volts into joules, we get the energy difference as 3.68 into 10 to the power of minus 19 joules. So using Bohr's frequency condition, the frequency of radiation emitted is calculated as nu is equal to E1 minus E2 by h, which is equal to delta E by h, where h is Planck's constant. So by substituting the value of delta E and h, we get the frequency as 0.555 into 10 to the power of 15 or 5.55 into 10 to the power of 14 Hertz. Thus, the frequency of the radiation emitted when an atom makes a transition from upper level to lower level, which have the energy difference of 2.3 electron volts, is 5.55 into 10 to the power of 14 Hertz. Let's move to the next one. A hydrogen atom initially in the ground state absorbs a photon which excites it to the n is equal to 4 level. Determine wavelength and frequency of photon. Now given energy in initial level N1 is En1, which is equal to minus 13.6 upon 1 square, is minus 13.6 electron volt. And energy in the final level, that is N2 is equal to 4, is En2 is equal to minus 13.6 by 4 square, we get it as minus 0.4 85 electron volts. The energy difference between the initial and the final level are En2 minus En1, which is equal to minus 0.85 minus of minus 13.6, which is equal to 12.75 electron volt. And it is this energy which is absorbed by an electron to get excited. So when we convert the energy in joules, we get it as 20.4 into 10 raised to minus 19 joules. So 20.4 into 10 raised to minus 19 joules amount of energy is being absorbed by an electron to make a transition from ground state to n is equal to 4 state. Now from Bohr's frequency condition, h into nu is equal to En2 minus En1. So therefore, frequency can be given as nu is equal to En2 minus En1 upon h, where h is the Planck's constant. So you already know the energy difference between the two levels as 20.4 into 10 raised to minus 19. By substituting the values, we get the frequency as 3.077 into 10 to the power of 15 hertz. And the wavelength can be given as lambda is equal to c divided by nu, where c is the speed of light in free space. Lambda is equal to 3 into 10 to the power of 8 divided by 3.077 into 10 to the power of 15. The wavelength is obtained as 0.97 into 10 to the power of minus 7 meter. So thus, the frequency and the wavelength of the photon which is being absorbed by a hydrogen atom to make a transition from ground state to n is equal to 4 level is calculated. Let's move further. Calculate the shortest and longest wavelength of Bohrs series of hydrogen atom. Given Rydberg constant R is equal to 1.097 into 10 to the power of 7 per meter. Now we know that the wavelength is given with the relation R into 1 upon n2 square minus 1 upon n1 square. For shortest wavelength, the transition must be from infinity to second energy level. So for Bohrs series, n1 is infinity and n2 is 2. So therefore, 1 upon lambda is equal to 1.097 into 10 to the power of 7 into 1 upon 2 square minus 1 upon infinity square. On solving, we get 1 upon lambda as 1.097 into 10 to the power of 7 into 1 by 4. And hence, lambda becomes 3.646 into 10 to the power of minus 7 meters. So this is the value of shortest wavelength that is being emitted in Bohrs series. Now what is the maximum wavelength? The longest wavelength is obtained for the transition from third level to second level, that is n1 is equal to 3 and n2 is equal to 2. So using the same formula, we have 1 upon lambda is equal to 1.097 into 10 to the power of 7 into 1 by 2 square minus 1 by 3 square. On solving, we get 1 upon lambda is equal to 1.097 into 10 to the power of 7 into 5 by 36. Hence lambda, we get it as 6.563 into 10 to the power of minus 7 meters. So the longest wavelength is 6.563 into 10 to the power of minus 7 meters. And these two wavelengths are subjected to Bohrs series of hydrogen atom. In this calculation, we have been given the value of R, Rydberg constant. So therefore, we could solve it very easily. Let's go on with the next one, where R value is not given. Now what we have here is, the first member of Bohrs series of hydrogen atom has a wavelength of 6353 angstrom knot. Calculate the wavelength and frequency of the second member of the same series, second member of the Bohrs series. We have been given the value of speed of light in air as 3 into 10 to the power of 8 meter per second. Now here, the wavelength of first member of Bohrs is given as 6563 into 10 to the power of minus 10 meters. Speed of light as c is equal to 3 into 10 to the power of 8 meter per second. We know that 1 upon lambda is equal to r into 1 upon n2 square minus 1 upon n1 square. For first member of Bohrs series, n1 is equal to 3 and n2 is equal to 2. So when we substitute, we get 1 upon lambda 1 as r into 5 by 36. We call that as equation number 1. Now, for second member of Bohrs series, n1 is 4 whereas n2 remains as 2. So it is a transition of an electron from fourth level to second level. So let us write it as 1 by lambda 2 is equal to r into 1 upon 2 square minus 1 upon 4 square. So the wavelength of second member of Bohrs series can be hence given as 1 upon lambda 2 is equal to r into 12 by 64. Let's call it as equation number 2. Now let's take the ratio of equation 1 and equation 2. So dividing equation 1 and 2 gives lambda 2 by lambda 1 is equal to 5 by 36 into 64 by 12, where r and r Rydberg constants gets cancelled. And hence lambda 2 can be further written as 0.74 into lambda 1. We already know the value of lambda 1. So therefore, if you substitute the respective value of lambda 1, we get the wavelength of second member of Bohrs series as 4856.6 into 10 to the power of minus 10 meters. We have also been asked to find out the frequency. Now frequency is nu2 is equal to c by lambda 2. C is given as 3 into 10 to the power of 8 and lambda 2 is calculated. So therefore, frequency of the second member of Bohrs can be given as 6.177 into 10 to the power of 14 Hertz. Thus, we have found the wavelength and the frequency of the second member of Bohrs series by taking account the wavelength of first member of Bohrs. At any cost, if r is not given in the question, you are not supposed to use it. So you have to reduce the solution such that you are going to cancel r at some point. So these were the numericals on the chapter atoms. If you have not understood any of the part, I suggest you to go to the previous videos and come back. So we finish up with the chapter atoms. Thank you.